So, hello everyone, welcome to the TCS seminar at Jagiellonian. Today our guest is Pierre Aboulker from École Normale Supérieure in Paris.
Exactly.
And Pierre will tell us about the Clique number of tournaments.
Yes. Well, thank you very much for the invitation. And I'm going to speak about Clique number of tournaments. And this is a union of published and unpublished papers. Altogether, those it's a result that I had together with Guillaume Aubian, Pierre Charby, Samuel Coulon, Stéphane Thomasset, and Raoul. So, I'm going to speak about coloring. So coloring of undirected graph, I assume everybody knows what it is. You want to color the vertices in such a way that two adjacent vertices receive distinct colors. And the chromatic number of the graph is the minimum number of colors that you need to do it. And the first question I ask is, how could we define coloring for directed graph? Maybe the first idea that you can have is you do the same, but in this case, the orientation of the edges will not have any any orientation of the edges will give the same chromatic number, so it's not very satisfying. And a concept that arose since a few years is the concept of dichromatic number. So this time you want to color the vertices in such a way that no directed cycle is monochromatic. So for example, this is not a directed cycle because this arc is not in a good direction, but this is. So this is a good two coloring of this digraph. And when you have two arcs in a digon like this, one arc in a sense and the other one in the other sense, then this is a directed cycle. So here you want two distinct colors. And so we define the dichromatic number of a digraph like the minimum number of color needed to color the vertices in such a way that there is no monochromatic directed cycle. And note that digraph with a dichromatic one are exactly acyclic digraph, and that admits topological ordering. That is an ordering where the arcs all goes in the same direction. Okay, so why is this a good notion? It is because it generalizes undirected coloring. Because when you have a graph G, like the difference between digraph and undirected graph is the symmetric of the adjacency relation. So in a graph, A is adjacent to B and B is adjacent to A. In a digraph, it might be A sees B, but B does not see A. So like the representant of a graph into the directed world is you replace each edge by a digon like this. So we call it the symmetric graph because it's symmetric. And it's easy to see that since those are two cycles, that cycles of length 2, the chromatic number of this is exactly the dichromatic number of this. So every time you have a theorem on chromatic number of undirected graph, you can translate it in the world of symmetric digraph. This is a digraph where every time there is an arc from A to B, there must be an arc from B to A too, and that the adjacency relation is symmetric. And you replace chromatic number by dichromatic number, and then you can ask, is the theorem true for every digraph? You want to generalize it. So this is also please feel free to interrupt me anytime you want, at any moment, as much as you want. I'll be glad to answer any questions. So in this way, so the dichromatic number has been introduced by Neumann, Lara, and Erdős in 1981, and some people, so they had some results, and then it was kind of forgotten. In 2010, Boyan Moa followed this line of research and tried to generalize theorem on coloring to digraph. we started with Brooks' theorem and Galai theorem, that are famous theorem in graph coloring, and since then many other theorems has been generalized. Okay, so this was to introduce the dichromatic number. So I will speak a lot about the dichromatic number. And now, okay, let's go back to undirected graph and ask the question, like the main question when you do coloring: why does a graph has large chromatic number? So an easy answer to that is because it has a large clique. So this is a simple answer, but it's only a partial answer because, of course, there is triangle graph with arbitrarily large chromatic number. And from this, you can which class of graph? This is the correct answer. Those classes of graph are called chi-bounded, and we say that the class of graph C is chi-bounded if there exists a function f such that for every graph in the class, the chromatic number is bounded by a function of the clique number. So now in this class, if you have very large chromatic number, the only reason why you can have large chromatic number is because you have large clique number. If the clique number is bounded, then the chromatic number is also bounded. So this is the notion of chi-boundedness, and so it comes from perfect graph. Perfect graph are the class of graphs that are chi-bounded by the identity. And then it has been generalized by first by Sumner, and then mostly by Gerfash in a very beautiful paper called Problem Surrounded Perfect Graph, I think. And so since then, chi-bounded classes has been studied a lot. Let me give you one conjecture and one result on chi-boundedness. So the first one is the Gerfash-Sumner conjecture. It says that given a graph H, the class of H3 graph, so here H3 means a graph that does not contain H as an induced subgraph. So this class is chi-bounded if and only if H is a forest. So this is still a conjecture. It has been proved for a few family of forests, but it's still widely open. And I think it can be considered as the main open conjecture in the theory of chi-boundedness. So I will speak about it later. And another theorem that I will speak about that is kind of folklore is if you have a chi-bounded class of graph C and you close it under substitution, it means that if for example, this is in my class, I can replace this vertex, any vertex, by any graph in the class where I do where every vertex 3 has the same adjacency as the vertex it replaced. So it enlarges the class, but this enlargement still gives you a chi-bounded class. And again, I will try to generalize that to digraph later. Okay, so this chi-bounded theory is now very rich theory, and we wanted to try to generalize it to digraph. So to do that, we need a notion of clique number of digraph. So let's think about that. What is the clique number of a digraph? Okay, ideally, what we would like. The property of the clique number should be first, it is a lower bound on the dichromatic number. So we want the clique number to be a lower bound on the dichromatic number. And we also would like that the clique number of a graph G is the same as the clique number of the symmetric of G to be able to generalize. So the first attempt, maybe the most natural one, would be for the clique number, take the size of a maximum symmetric clique in D. So for example, if you have this digraph, the clique number would be 2, because there is a symmetric clique here of size 2, but nothing else. So this is nice, but the thing is, if there is no digon like this, we call those digraph-oriented graph, then the clique number is 1, and this is a family very complicated. So it's not very satisfying. Still, this notion has been used in one paper where they generalized the perfect graph theorem to digraph using dichromatic number and this notion of clique number. Up to my knowledge, this is the only paper where this is used. A second attempt, maybe less natural, maybe but interesting too, I think, is to take the size of a maximum transitive tournament in D. So maybe I forgot to say what a transitive tournament is. Transitive tournament, it's you have every between each pair of vertices there is an arc, and you can order the vertices so that every arc goes in the same direction. And so you say, okay, the Clique number of a digraph is the size of the largest transitive tournament. So this does not give you a lower bound on the dichromatic number, because, for example, the transitive tournament of 4 vertices, its Clique number is 4, and the dichromatic number is 1. There is no directed cycle. So it fails to have this, but I wanted to mention it because it was studied, and in particular there is a nice conjecture that we proposed with Pierre Charby and Rezan Aseras that says the following: given an oriented graph H, so oriented graphs mean no digon, then the class of H3 oriented graph is chi-bounded using dichromatic number and this notion of Clique number, if and only if H is an oriented forest. So this really looks like the Gear-Fashioner conjecture. But this is even more open than the Gear-Fashioner conjecture. I think it's open even for directed path. When H is a directed path, we are not able to do it. So we know, like for triangle 3, P7-3 oriented graph, we know the dichromatic number is bounded, but this is further we could go. Anyway, I don't want to talk about this notion. I want to introduce a new notion, a third one. So because this one is not entirely satisfying, because it's not a lower bound on the dichromatic number. So let's try to find a new one. So to define the new one, I will need another concept that is quite central in tournament theory, in digraph theory, is the concept of package graph. So it's like this: if you have a digraph D and an ordering on the vertices, so you put the vertices in a line, there is the arcs that goes forward and the arc that goes backward. Okay, so it partitions the arcs in two sets. I'm going to define the package graph of D with respect to this ordering like this. I delete the forward arc and keep only the backward and forget their orientation. So this is an undirected graph. But it's an undirected graph that a lot of properties of the digraph are transferred to this package graph, as we're going to show now. Okay, so this is the definition of the package graph. So this is also a notion that I will use all along the course, the seminar. Okay, first observation is that if D is acyclic, then it has a ordering of the vertices where all arcs goes from left to right, and so the package graph is a stable set, has no edge, and it's an if and only if. Okay, now I'm going to say why the package graph is very related to the digraph. So the first easy property is that for every ordering of D, I have that the dichromatic number of D is at most the chromatic number of the package graph. So why is that? Okay, because take a coloring of the package graph. Let's look at here and look at the color class in the package graph. Say this is a color class. It means that this is a stable set in the package graph. So every arc goes from left to right or forward. So it is an acyclic subdigraph of D. So it can also be used as a color class of D. So a coloring of this give a die-coloring of this. Okay? Good. And the second thing is that there exists an ordering such that the opposite holds. The chromatic number of the package graph is at most the dichromatic number of the digraph. So if you look at all the package graph and you look at the one that minimized its chromatic number, you have the dichromatic number. And this ordering is very easy it's very natural ordering. Take a decoloring of the digraph and order the vertices like that. First put every vertex colored 1, then every vertex colored 2, then every vertex colored chi of v. Each of those is a acyclic subdigraph. So I can order those such that everyone goes forward. So those are stable set in the package graph, so they are also color class of the package graph. Okay. So it gives me an equivalent definition for the dichromatic number that goes defined through the package graphs. And now that we have this definition, well, we replace chi by omega, and we have a notion of clique number. So we define the clique number of a digraph as the minimum of the clique number over the package graphs of these digraphs. Okay. And now the goal, so this satisfies the two properties that we want. First, if you take the clique number of a graph G, if you look at it symmetric, well, when you have a symmetric digraph, between every vertex, between every pair of vertices, there is an arc in both directions. So in the package graph, there will be x and y will be always adjacent. So actually, symmetric digraph, there are only one package graph, which is G. So this is good. And omega is at most chi because for each package graph, chi is at least omega, so the minimum is also at least. So it has the two good properties. So let's investigate this concept, see if it is nice or not. Can say also right now that since it behaves, the package graph of a symmetric digraph is always the same. Actually, I can do the same trick with any graph parameter. If I, instead of chi or omega, I take something else, then I have a directed version of a graph parameter. And maybe there is some funny thing to study here. For example, if you took vertex cover instead of clique number, then you retrieve a feedback vertex set. There is some stuff like this. Also, if you replace by maximum degree, then it has been studied as a parameter to solve a parameterized problem on tournaments. It has also nice properties. But anyway, today let's just do a clique number and dichromatic number. Okay, so first I'm only going to speak about tournaments. So what is a tournament? It's an orientation of a complete graph. So between every pair of vertices, there is exactly one arc. So why do I do that? First, because it's simpler than a digraph. And the topic is already hard enough. And also there is good reason to think that they are more interesting to study than digraph. And the reason will come in a few slides. Okay, so now I will just speak about tournaments. Tournaments, I will speak a lot about C3. C3 is the directed triangle. So it's easy to see that if you want to dicolor a tournament, the color class needs to be acyclic, and for a tournament, being acyclic is exactly being C3 free, which is exactly being a transitive tournament. So transitive tournament TTK is the unique tournament on K vertices that has no C3, and dicolor tournament is the same as color the vertices such that no C3 is monochromatic or partitioned into transitive tournaments. Okay. Now let me give you the construction of tournament with arbitrarily large dichromatic number to start to play with the notion, and because this family will be used afterwards. So S1 is just a vertex, S2 is a directed triangle, and then you define recursively Sk. You take 3 copies of Sk minus 1. Oh no, only 2. You take 2 copies of Sk minus 1 plus a vertex, and you organize them in a triangle fashion. So you put every arc like this, every arc like this, and every arc like this. Okay, and I claim that chi of sk equal k. Why is that? So it's true for S1, assume it is true for sk minus 1, and try to color that with k minus 1 colors. Then you need all the k minus 1 color for this copy of sk minus 1. Here again, you need the k minus 1 color. And here, what do? If you put color I, if color I appear here and here, then you have a monochromatic geometry triangle. So here you need color, a kn color. So this is a typical tournament family with large dichromatic number. Okay, and we note it like the delta of tt1 sk minus 1 sk minus 1. Delta of tt1 sk minus 1 sk minus 1. This is a drawing of S3 because the first question that we asked when we defined this clique number is how those tournaments can have arbitrarily large clique number. And well, this is an ordering of S3 here, so that this is this has dichromatic number 3, but the clique number actually is at most is exactly just 2. There is a numbering of this, an ordering of this, so that there is no triangle. There is a C5 because the chromatic number must be at C3. But no triangle. Okay, this is not very important. So let's go back to clique number. So the only tournament with clique number 1 are acyclic tournaments. So they are transitive tournaments. Because if you have a directed triangle, when in any ordering of this, there will be always a back edge. So the clique number will be 2. So omega C3 equal 2. So omega of t equal 1 if and only if it's a transitive tournament. It is at least 2 if and only if it contains a C3. And I can say it right now, the complexity of deciding if omega of t is at least 3 is open. At least 4 is hard, but at least 3 is still open. Okay, first very easy property of clique number, it behaves on strongly connected component as the clique number behave on the connected component. If I have, say, 2 connected components, A, B, so say every R goes from B to A, from A to B, then I can first put the vertices of A, then the vertices of B, and in the package graph, there is no edge between those two. So the clique number of this is the maximum of the clique number of A and B. Good. And now another property that I will use, that we used in every proof of, and every proof that we have, we called it the fundamental inequality. So it was proved before, so we introduced this clique number of tournament 1 year, 18 months ago. But it appeared already in a paper by Nguyen, Scott, and Seymour, where they don't define the clique number of tournament, but they look at the clique number of package graph of tournaments. So they play with the idea. And they prove the following. So what does it say? That for every ordering and every tournament, let me write it like this. Okay, so it mixes tournaments and undirected graph, and it mixes chromatic number, clique number, and dichromatic number. But it's not that hard to understand anyway. So we know that, so it gives a lower bound on, it said that the chromatic number of the package graph is at most the dichromatic number of the tournament times the clique number of the package graph. And let me tell you why this is super useful. Because there is a natural way to build a tournament from an undirected graph. Let's say, take a graph G that is, say, triangle free, and chi of G is large. Then put any ordering on the vertices of G, and we're going to make a tournament out of G. The edge of G, orient them backward, like this, and the non-edge, because I want to build a tournament, the non-edge add an arc that goes forward. Then by construction, this is T and T prec. For the back-edge graph of T with respect to an ordering, I call it T prec because this in LaTeX is prec. So this is, I'm sorry for that, but I'm used to it now and I cannot correct. So the back-edge graph of T is exactly G by construction. And now I know that because of this inequality, I know, or maybe this one more, it's the same, but I know that the dichromatic number of T is at least chromatic number of the back edge divided by clique number of the back edge. But since the back edge is G, this is equal to 2, and this is equal to large. So the dichromatic number of this tournament is large. So this is a way from an undirected graph G that is triangle fair and large chi, I can build a tournament with clique number 2 and large chi. So this is useful. And the proof is easy. I can show you the proof. So take the tournament and the ordering that is given with the tournament and color it with chi of T colors. And now look at the color class of the dicoloring. This is a color class of the dicoloring of T. So this is a transitive tournament, but the ordering is, I have no control on the ordering, so there is edge in both directions. And I'm going to color the back-edge graph induced by those vertices with this number of colors, which will give me a coloring of the back-edge graph T with this times this number of colors. And how do I do that? Well, the clique number of this is omega, so I want to color it with omega colors. Okay, one way to see it is that this, since it is a transitive tournament, this is exactly a permutation graph, which are perfect graphs, so they can be colored like this. Or you can go straight for, like you can give a coloring. You take, for each vertex, take a longest path that goes from right to left and ends in this vertex. This is 1, 2, 3, 4, so this will receive 4. First, any vertex that is adjacent to it in the back-edge graph, it will have not the same length path, so it will be a coloring. And this path, since this is a transitive tournament, all arcs must be like this. So this is a clique in the back-edge graph. So the length of a path is at most the clique number of the back-edge graph. Okay? And yeah, I call it, well, I'm the only one calling it fundamental inequality, but I call it like this because this is what makes everything work. And for example, if you replace tournament by digraph here, this is not true anymore. And this is the reason why we study tournament instead of digraph. Okay. So first application is construction of interesting tournaments, and this is an example. Tournaments with large dichromatic number and small clique number. Okay. Is there a question? Maybe? No? So more vocabulary. Let T be a tournament with an ordering on the vertices, and omega ordering is an ordering that the clique number of the back-edge graph is the clique number of the tournament, and the chi ordering is an ordering that gives the dichromatic number.
Well, I have a question.
Yeah.
So you presented some kind of canonical way of writing a dichromatic number of tournament up, right?
Yes.
So this is the example.
This?
Oh, this. Oh, even this one, yeah.
Yeah.
Aha. And this was yet another one. So I was thinking that if you forbid these canonical examples, can you get the chromatic number out? But probably you answered already.
Yeah. So okay. So actually, your question is, if I forbid this, there's a bound dichromatic number of tournaments. So this was answered by Scott, Seymour, Thomasé, Lebel, Chernesky, and Berger,
okay,
that characterize exactly the tournament H, so that H3 tournament have bounded dichromatic number.
What is the characterization?
It's I will give it later, but this is there is only two families. Like any such tournament must be contained in one of those SK. and they also must be contained in one of those. And the intersection of those two gives the characterization.
Oh,
it's very nice. Yeah.
Very nice.
Then the proof is not easy, but this is the only two family that they looked at. Okay, what did I want to say here? I want to say that because of the fundamental inequality, which is here, every omega ordering gives a good approximation of chi. So it's just if this is an omega ordering, then the chromatic number of the Backes graph is not too large. It's not too large compared to the dichromatic number. And it's just a straightforward application of the fundamental inequality. But I think this is something deep. This is why it works well. Because when you have an omega ordering, you can work on the Backes graph and it kind of give you the chromatic number.
And omega ordering is the ordering with the same omega, yeah?
Yes. Okay. And omega ordering is when you look at the Backes graph, the clique number of the Backes graph is minimized the clique number over all the Backes graph. And here you say this is at most, maybe a step is missing. You say that the chromatic number of the Backes graph is at most this, clique number of the Backes times the chromatic number. But this is exactly the clique number of the tournament, and the clique number of the tournament is at most chi, so this is at most chi squared. Okay, so maybe I can skip this. This says that there is chi ordering that does not give a good approximation of omega. They are quite easy to find. But what we don't know is there always an ordering that is both an omega and a chi ordering? So the answer should be no, but I would like to see an example. I see no reason why this should be true, but it's hard to produce a counterexample. Okay. Next question is, can you find tournament with large clique number? Good question. Otherwise, well, the answer is yes. And let me give you the family again. So it's a family that, so actually this family works, because actually the clique number of those is large. But this is not easy to prove. Not very hard, but not easy. So let me give you a simpler one. It looks like this. I call it the BI. You take B1 is just one vertex. B2 is a directed triangle. And you recursively define them like this. This time, you take 3 copies of BK minus 1 and you organize them in a triangle shape. And I claim that omega of BK is at least k. And the proof is very easy, because so I want to prove that for every ordering of this tournament, the Backes graph has a k-clique. So I take any ordering and look at the first vertex of the ordering. The first vertex is either here, here, or here. That is the same. Assume it is here. And in its in neighborhood, there is a copy of BK minus 1. And by induction, this has omega at least k minus 1. And all those are packaged. So when you add a vertex, you have plus 1. So this is the most simple argument to prove that the tournament has large clique number. Kind of degeneracy. And we were not able to compute what is the clique number of Bn. So in particular, we proved that Bn has clique number at least n, but the number of vertices of Bn is 3 to the n, so it could be way larger. We can prove that the clique number is at most this. So maybe yesterday we decreased a little bit this bound, but it's still very far away from n. And this is in relation with a natural question that would be, what is the smallest f of n such that every n vertex tournament T has omega at most f of n. So I give you an n vertex tournament what is the maximum clique number it can have. It cannot be n, because if it is then it should be a transitive tournament which has clique number 1. So I don't know what it is. The best bound I have for f is a log, is logarithmic. So it's certainly not true. It certainly should be polynomial in n. I know that there is n vertex tournament with clique number logarithmic in the number of vertices. This one, exactly. But I don't know anything else. And I think random tournament, because normally the answer to that is random tournament, but random tournament has clique number of logarithmic size. I'm 99% sure of that. I never wrote the proof, but it's easy. So this is an open question, these two. Me, I think that this is a good candidate to have large clique number, but I could be wrong. Okay. Okay, now I link this clique number with another digraph parameter, which is domination number. So the domination number is the smallest set of vertices that sees every other vertices. So out neighbor of this union this is the whole tournament. And it's easy to see that this is a lower bound on omega, because if you take any ordering, you can build a dominating set like this. You put this in your dominating set. So it's going to dominate some vertices, and at some point it does not. So this is not dominated by this, so I put it in my dominating set. So this is a package then, with respect to this ordering. Then I continue, and maybe some guy is not dominating neither by this, neither by this. So it means that I have this and this. I put it in my dominating set. And what I'm constructing here is a clique. So I always, for every ordering, I have a dominating set of the size of the clique number. So it's a lower bound. Okay. Okay. Now the main topic. Well, maybe the main topic is a chi-bounded class of tournaments. So we say that a class of tournaments is chi-bounded if, well, the usual definition, if for every tournament in T, the dichromatic number is bounded by a function of the clique number of T. So which class of tournament are chi-bounded? So the first theorem that we proved, that I'm not going to prove here because it's not easy enough, it's too long to be proved on board, is that if you have a class of tournament that is chi-bounded, if you close it by substitution, it's still chi-bounded. Okay. Another question we could ask is, because Chetowski, Pellas, Scott, and Trottignon prove that if a class of undirected graph is polynomially chi-bounded, so chi-bounded by a polynomial function, then its closure under substitution is also polynomially chi-bounded. But this is harder to prove, and we could ask, is it still true for tournaments? I suspect it is not, I would say. And only for this question, it might be that it is true for class of digraph instead of tournaments, because we use the fundamental inequality to prove this, that we cannot use here, but we can see that there is some space, and well, this I could believe that this could be true. Okay, so that was the first result. Now I want to link classes of undirected graph with classes of tournaments. So given a class of tournament, we denote by this T-prec the set of all package graph of each tournament in the class of tournament. So for each tournament, there is n factorial package graph. So when I have a class of tournament, it gives me a class of package graph, which is a class of undirected graph. So for example, if you think about it for a little bit, if you look at package graph as transitive tournament, it exactly gives you a permutation graph. And there is a lot of things like that. It's funny. You can also go in the other way around. You take a class of undirected graph. For each undirected graph, for each ordering of each undirected graph, you can have a tournament with the classic technique, and it gives you a class of tournaments. And this is used actually to build interesting class of tournaments. And one can prove that the class of tournament is chi-bounded if and only if its class of package graph is chi-bounded in the usual way. It's an if and an if. And the proof is super easy. It is, you write definition, you apply the fundamental inequality, and you have the proof in both directions. Okay, so I put it here to show this bridge between the undirected world and directed world, but we don't really use it, actually, this if and an if thing. So this is the proof, as you can see, that's very easy. Let me skip it anyway. Okay, now the big question. Given a tournament H, we denote by form of H the class of tournament that does not contain H as a subtournament. So it's a natural way to define classes of tournaments. And the question is, for which tournament H, form of H is chi-bounded. So for such tournament H, we say they are chi-binding. And some are not, most are not. And let's investigate. Okay, so this is the question. First a little, well, the simplest case of chi-bounding function that does not appear in the undirected world is the constant function. And we are back to the graph tournament we spoke about. So if you are chi-bounded by a constant function, it's the same as for which tournament H there is a number CH, so that every H3 tournament has a dichromatic number bounded by this number. So this was studied before the Clique number of tournament was defined. And such tournaments were called heroes and was characterized by those guys 10 years ago, 12 years ago. So let's investigate them for 1 minute. So for example, if you take C3 tournament are exactly transitive tournament, so C3 is a hero. If you take a transitive tournament, well, if you look at tournament with no TTK, with no transitive tournament of size k, those tournaments have size at most 2 to the k by Ramsey, so they are bounded dichromatic number by just 2 to the k. It's a finite set. And they prove that all the heroes can be built like this. The vertex is a hero. If you take 2 heroes and push all arcs in the same direction, you get a hero. And the last way to build a hero is you take a vertex, you take a hero, you take a transitive tournament, and you organize them as usual now in a triangle fashion. And this is a hero. And all heroes are built like this.
And you direct them either one or the other way?
Yes. The direct triangle is in both directions. True. And the proof is quite hard. The first proof was quite hard, and since then there has been at least 3 papers that were simplifying the proof, and now it's not so hard anymore. But still, it's still not trivial at all. Okay, so seeing this, we were wondering, we define a gentleman. So gentleman would be hero tournament H, so that when you forbid them, the clique number is bounded. And we could characterize them easily because with a little trick, well, we can prove that they are the same as heroes. So that was nice. Let me also skip maybe the proof. It's not so interesting. Okay, so now let's go back to the question. For which tournament H, for both H is chi-bounded. So for heroes, they are chi-bounded by the constant function. But, okay, there is more to say. Okay, what I can say is that if H is chi-binding, if form of H is chi-bounded, then there exists a numbering of the vertices of H such that the package graph is a forest. So this is a Riemann fashion. And the proof is easy. It's again a corollary of the fundamental inequality. So take a graph tournament H, so that for every ordering, the package graph has a cycle. And you want to prove that form of H is not chi-bounded. Let's show it. Take a graph, undirected graph G, with girth V of H plus 1, size of this plus 1, so very large. And chi of G as large as you want. This exists by Hölder's theorem. Now, put any ordering on the vertices and transform this graph into a tournament in the usual way. The edges of G, you orient them backward, and the non-edge, you add an arc that goes forward. So I have, so this is T, and T, the back-edge graph is G. So first I claim that this tournament does not contain H, because take V of H vertices, and look, let's check if it is a copy of H. Well, the package graph is defined by this is an induced subgraph of G, so it has no cycle, so it is a forest, it cannot be H. Okay, so it is in the class, and the dichromatic number of T by the fundamental inequality, it is at least the chromatic number of the package graph here is G, or this package graph, divided by the Clique number of G. This is large, this is 2, so this is large. So there is a tournament in my class that has Clique number 2 and dichromatic number arbitrarily large. So the class is not chi-bounded. So the proof is exactly the same than the proof that in the undirected setting you need to forbid the forest, and the property is transferred by the fundamental inequality. So this is what I wrote here, in case I was forgetting. Okay, so recall the Gear-Fashioner conjecture. If H is a graph, then the class of graph that does not contain H, that forbids H, is chi-bounded even if H is a forest. So once we have that, it is very tempting to say that the same holds for tournament. Form of H is chi-bounded even if H has an ordering such that the back-edge graph is a forest. And unfortunately, this is very, very, very false. So we submitted the first paper we had, we did this conjecture, and a few months later, my PhD student found a counterexample, a very small one. So why is it heavily false? Well, because Guillaume Aubion find a 5 vertices tournament that is not chi-binding, and that is a forest, that admit a forest ordering. And since then, many others were found by another student of mine internship. And the method to find them is familiar to some people here. It's kind of natural. You take a construction of triangle-free graph with large chromatic number, like Blanche-Descartes, one that we used. Then you order the vertices, so this is the Blanche-Descartes graph, the triangle-free with a chromatic number large. You make a tournament out of them with this technique, and you prove that the target tournament that you are looking at does not appear as a subtournament, and you win. So it's a little game that we can play, and we played it and find a lot of counterexamples. Okay. On the positive side, what we know is that if you take two chi-binding tournaments, and you take a copy of one, copy of the second, and put all arcs in the same direction, it is still chi-binding. What we also have is that if you take an arc, a copy of H, where H is chi-binding, and you organize them kind of usual, triangle fashion, then this is also a chi-binding tournament. And this is a corollary of a hard theorem by Newman and Clique and Felix, I don't know how to pronounce, that says that, like when you take an arc, we define the neighborhood of this arc as the set of vertices that form a triangle, geometric triangle with this arc. And they prove that if in a tournament the neighborhood of every vertex has bounded dichromatic number, then the whole tournament has bounded dichromatic number. And now, if you take a tournament that does not contain this, where the neighborhood of every arc is H3, H is a chi-binding, so the neighborhood has bounded dichromatic number, so the whole thing has bounded dichromatic number. So we tried to prove that, and at the same time, Felix and Alanta proved this, which is stronger than what we needed. So this is a way to build a tournament. So a corollary of a result by Briansky, Davis, and Bartosz is that if the tournament has a matching as a package graph, then it is chi-binding. So I will come back to that later. And this is just an observation. If you have a tournament that is chi-binding and you reverse all arcs, it is still chi-binding. And this is actually a corollary of this. Okay, so this is what we know. I wanted to give the proof that if H1 and H2 is chi-binding, then so is H1 row H2. But let me skip it first because well, the proof that we had is a bit complicated, and the discussion with Bartosz 2 days ago showed me that there was a very simple proof of that.
Show the simple one.
Huh?
Show
Yeah, the simplest one is just the use of a superclassic argument that we missed. So here, what was nice here is that we use technicality that are used very often in all the proof. So it kind of showed what kind of technicality we use. But I don't know how much time do I have? 1 hour, a bit more? Do you want some technicality, or there is already enough?
We can have some technical.
Yes? Okay, for Piotr. Okay, so let's try. So you have H1, H2, and you want to prove that if I forbid this, then the class is chi-bonded. Okay, so let's try. So we do it by induction of omega. So there is 2 steps I wrote. So the first step is if I have an arc x, y, I look at its neighborhood, so the set of vertices that form a triangle with this arc. And if this has large dichromatic number, then in every omega ordering, y should come before x. This should be a bucket. And this is something that we use very often. Do it by contradiction. So assume x is before y. Say that this is the set of vertices x. So those vertices, some of them are here, some of them are here, and some of them are here. So the union of those 3 boxes is x. But I assume x has a very large dichromatic number. So one of those 3 boxes has large dichromatic number. And by induction, it means that one of those 3 boxes has omega, same as the whole tournament. And now look at the package. Y sees big X. So it means that this is a package. This is full package, full package. So if the clique number here is the clique number of the whole tournament, it's a +1 contradiction. Same here. And now we know that X sees little x. So we know that also this is full package. So also this has the clique number at most omega -1. So it must have small dichromatic number. I have the contradiction. Good. So now we call those heavy arc. Those are arcs that in the neighborhood there is large dichromatic number. And the other one are light arc. Okay. And now I'm going to prove that if I look for each vertex, if I look at its out neighborhood and its in neighborhood, one of those two sets has small dichromatic number. And this will be enough to finish because of this theorem, very important theorem by Namle, Arat, Arutunian, Stefan Thomaset, and Wu, that said that for every tournament, if the out neighborhood of every vertex has bounded dichromatic number, then the whole tournament has bounded dichromatic number.
How do you prove that one?
This one is 1 page and a half, but very, very smart. Like for when t equal 1, I think it's easy. When t equal 2, there was a 15 pages long proof by Seymour, Chernovsky, I think Thomaset too. And then they came up with a 2-page proof, very, very, very elegant.
You should have in the evening.
No problem. Have to revise a little bit, but okay. So now to bound the dichromatic number of a tournament, it's enough to bound the out neighborhood of each vertex or the in neighborhood. Then you partition in 2 sets and it's okay. So we want to prove this. So this is the difficult part. Take a vertex x and you want to prove that in or out neighborhood is small with a dichromatic number measure. So first, I think I look at, for example, the in neighborhood such that this arc is heavy. And the out neighborhood such that those arcs are heavy. Then it must, in the omega ordering, it must be like this. This heavy arc, they are all packaged.
Yes.
Okay, so this, the clique number here, must be omega minus 1. So the dichromatic number is small, same here. So those heavy arc, they are, we don't care about them because of the step 1.
Mm-hmm.
So now let's look at light arc. So I have x, I have the in neighborhood here and the out neighborhood here, and those are light arc. So if this has large dichromatic number, then it must contain, I would say, H1. I can choose between H1 and H2. I think I need H1 because H1 free graph, H1 free tournament are chi-bounded, and here the clique number is bounded. So here I have a copy of H1. Now, if I look at the, let me take H2, I think. Okay, we'll see. So those two have large dichromatic number. Look at the out neighborhood of a vertex in here. Its out neighborhood here. This is contained in this form a triangle like this.
So it's a small dichromatic number.
So it has small dichromatic number because it's a neighborhood of this arc and this arc is light. So I can, for each vertex of H2, I can delete its out neighborhood here. It gives me H2 set of small dichromatic numbers, which is small. Now the rest, well, by definition, is full to H2.
And it must contain H1.
So it is H1 free, so it's small too. Yeah. So yeah, this is typical kind of arguments that are used in all those things. This argument appeared almost like this in the Heroes paper. It's very, very, very nice. Okay, but there is a 2-line proof with the usual. The proof to prove that in Geerfashoner, it's enough to prove Geerfashoner for tree instead of forest, but almost the same proof works here too. Okay, this I want to skip. This I can talk about it very quickly. So this is, so given a tournament H, we can define the following set of ordered undirected graph. Like for H, you look at all the Backes graph, and Backes graph come with a natural ordering, of course. So this gives me ordered Backes graph. So it has n factorial ordered Backes graph. And by the fundamental inequality, the direct corollary, we have that form of H is chi-bounded if and only if. So this is a class of ordered graph that does not contain any of those ordered graphs, any of the ordered package graphs of this guy. And we said that this class of tournament is chi-bounded if and only if this class of ordered graph is chi-bounded. And now, since Bartosz, Marcin, and James Davis proved a lot of things about ordered graph, we can translate the result to tournaments, and this is how we know that. So this is the result of Bensky, Davis, and Borchak, that if this is an ordered graph of maximum degree 1, then when you forbid it, it's chi-bounded. And now we know that if a tournament H has an ordered package graph that is a matching of maximum degree 1, then this is chi-bounded, and so this is also chi-bounded.
How do these tournaments look like?
How do
these tournaments look like?
Well, they look like this. And all the other arcs in the other direction.
Oh,
But,
okay.
I cannot say any smarter thing than this. They are two colorable and have clique number 2. And yes, this is an adventurous conjecture that maybe the only chi-binding tournament come exactly from the ordered graphs that are chi-binding. This will mean that H is chi-binding if and only if there exists an ordering of H such that this ordered package graph is chi-binding in the world of ordered graph. Well, I have no idea if it is true or not, honestly.
But as far as I understand, it's pretty much hopeless to understand which ordered graphs are chi-bounding.
Really? There is only 3 open cases.
3 minimal.
3 minimal. This you ask to Marcin and Bartosz. I agree with them. Anything they say. Maybe. Okay. But it's a hard question. It's not so amazing that it is hopeless to answer it. Okay, so now some link between tournament and undirected graph again. Maybe one of the most famous conjecture in graph theory is the Erdős-Reinhardt conjecture. Well, at least in the world of induced subgraph. If H is a graph, the conjecture says that there exists a number CH, so that every H3 graph has either a clique or a stable set of polynomial size in the size of G. So we know that if we forgot to forbid H, then there is a graph, random graph in particular, that has maximum clique number and maximum stable set of size log, logarithmic. So here it's polynomial, it's way larger. So this is wide open, but there has been some advances those past 2 years. And in 2001, Alon, Parr, and Solimosi give an equivalent way of stating this conjecture through tournament. So the tournament version is, if H is a tournament, there exists a number CH, so that every H3 tournament has a transitive subtournament of polynomial size in T, in number of vertices. And this is equivalent. And we could prove that, but this is not surprising, it did not come as a surprise, that if H is a tournament, and that form of H is polynomially chi-bounded, then H has the Erdős-Reinhardt property. And the same result exists on undirected graph. If H3 graph is polynomially chi-bounded, then it has the Erdős-Reinhardt property, and the proof transfer in tournaments for always the same reason, fundamental inequality. Okay. And now a less famous one, but I like very much this conjecture. It's the Erdős-Elzár conjecture from 1985. And it says that if the chromatic number of G is way larger than omega, then you can find So if chi of g is way larger than omega of g, then you can find two subgraphs A and B, so that there is no edge between them, and chi of A is large, and chi of B is large. The large here depends on the gap between chi and omega. This is very nice. Recently, Seymour, Scott, and Nguyen had a nice result on it. I think they can prove that they find this, but instead of large chromatic number, they prove, I don't remember what, maybe large average degree, something like this, something we can. What?
On one side. Yeah.
On one side, yes. And the other side, large chromatic number, I think. Okay. And still Scott, Seymour, and Nguyen, Scott, and Seymour, they proposed a seemingly unrelative conjecture on tournaments. It says that if a tournament has very, very large dichromatic number, then you can find two subtournaments in it, T1 and T2, such that dichromatic number of T1 is large, of T2 is large too, and all arcs goes in the same direction between those two. So they propose this conjecture and prove that this conjecture implies this one. And a few months later, Alan Newman and Felix Klinger-Fowler proved the other direction. So actually, those two conjectures are equivalent. And most people think that this is false. But before we knew it was equivalent, most people think that this was true. So we don't know anymore, I would say. And why do I speak about that? Because we proved that a class of tournament, if a class of tournament is chi-bounded, then it has this big property. The inside of this class, if I take a tournament with a very large dichromatic number, I can find those two guys. And here the proof is not easy. Okay. This would be, I think, the last part of the talk. I speak about clusters. So this is a new collection of problems on tournaments.
If it's chi-bounded, then large chi implies large omega. And if I have large omega, then I can just take two pieces of this omega, and this should prove it, no?
No, because the omega induces a transitive tournament.
Okay.
The proof used this notion of cluster. I don't want to go in the detail because I don't remember. Okay, so let me speak about cluster. That is a notion that has been studied since a few years in tournaments, and it makes a relation between two digraph parameters, tournament parameter. So given a tournament parameter gamma, a gamma cluster of a tournament T is a subtournament X of bounded size with large gamma. I will give example and it will be clearer, but the question is for which parameters gamma 1 and gamma 2 we have that if a tournament T has very large gamma 1, then it has a gamma 2 cluster. So let's give an example to the first result in this direction that was proved. It was again by Thomas Seller, Routinian, and Wu, by the same paper that the local to global. It's actually a corollary. So the following state that large domination number implies a chi cluster. So to put it formally, there is these two functions f and l, such that for every k, this will be the dichromatic number of the cluster. Every tournament T that has domination number very large, f of k, contains a subtournament X of size L of k, so the size of X does not depend on the size of T, and dichromatic number k. This says that if dom of T is very large, then I can find a subtournament X of bounded size, and chi of X is large. Like locally, at somewhere, there is a subtournament with large dichromatic number. This was very nice, and the strong result that I told you earlier is a corollary of this. This local to global said that for every tournament, if chi of the out neighborhood of x is at most t for every x, then the dichromatic number of the whole tournament is small. And this is a corollary of this, because if the tournament has small dominating number, so it has a small dominating set, then the whole tournament is covered by the out neighborhood of those guys, but the out neighborhood of every guy is supposed to be small. So the tournament has small dichromatic number. So we know that we can assume that the tournament has large dominating number. But then I found a chi cluster. So that would be a set X of bounded size, such that chi of X, and I take it with chromatic number t plus 1. And now, since this is of small size, this is not a dominating set. So if it's not a dominating set, there is some vertex that it does not dominate. Vertex X. But it means that this is in the neighborhood of X, but this has the chromatic number t plus 1 contradiction. So this is how they prove this. And they claim that actually this is maybe more interesting than this. Okay, and now we looked, well, some other people also look, if you replace domination number and chi by other parameter, what happens? So remember that we have this chain of inequality. Dominating number is at most omega, is at most chi. And we just said that large domination number implies a chi cluster. If you replace domination number by dichromatic number, if you have large domination number, you automatically have large dichromatic number. It's not true the other way around. And this is false. You can have a large dichromatic number with no chi cluster. And this is, for the construction, you just take an undirected graph with very large girth and large chromatic number, make a tournament out of it, and every bounded size subtournament will be forest. You cannot have a large chromatic number. But they conjecture that maybe this is true. Large domination number implies a dominate DOM cluster. So it means that we know that locally there is a subtournament with large chi, but large chi does not imply large dominating set. So they say, okay, maybe we can find a small subtournament with large dominating number. So this was open, and since we have a new parameter that is in between, we have new conjectures that are easier than the existing one. So this is a weaker version of this conjecture. Domination number implies an omega cluster. If the cluster that we find has large dominating set, domination number, it has large omega. So this is harder than this. But this is also open. And this, we would like it a lot, because if this is true, then we have this local to global property for omega. That is, if this is true, then it's easy to show that if a tournament T, every out neighborhood has small clique number, then the whole tournament has small clique number. And this looks like something that should be true. Okay, last thing, last conjecture, very nice conjecture. So we saw heroes and gentlemen, and now we are going to see a rebel. So tournament H is a rebel if it bounds the dominating number. So H3 tournament.
There's a question. So these clusters. So in the chi-boundedness stuff, people study if you have a large chromatic number, maybe you have a witness with a small radius set.
Yes.
Yeah, there are these. I forgot the name.
Control.
Control, yeah, like you have a K-controlled and then so it's not about the size but about the radius of the thing you look at, and there is a lot of research there.
Yeah.
So perhaps you could see a parallel stuff as well.
Yes, I didn't think about it.
So
I'm not super familiar.
Like a multiple step domination.
Maybe.
That you can make
Yeah.
two
But in tournaments,
Yeah.
maybe there is
It's not
something
concrete, I know. But,
distance in the two. Yeah. Or maybe we need to look at in the back to look at it in the package graph.
maybe in the back.
Because in tournaments you cover everything
Yes,
quite quickly.
yes.
I think. Yeah. Okay, thank you. Okay, so last conjecture, the rebel conjecture. So a tournament is a rebel. Tournament H is a rebel. If there exists a number CH, such that H3 tournament has domination number at most CH. So this has been a little bit studied, and post-set tournament play a role here. So post-set tournament, there is several possible definitions, but a post-set tournament is a tournament that has a package graph that is a comparability graph. But you can also define it maybe more naturally, that if you have an arc xy and an arc yz, then you must have the arc xz. This is equivalent. Like package graph. So an adventurous conjecture again by Chernovsky, Kimil, Seymour, and Thomasé is that a tournament is a rebel if and only if it's a post-set tournament. And they prove the only if part.
Wait, I don't understand something. Right? This property just implies that the tournament is transitive, right? Isn't it? Or I don't understand what you have just.
Oh. The directed triangle have. Oh. Right. This is not the good definition. I think, okay, I thought it was working, but maybe I'm wrong then. So I think the classic definition is that you can have a circular ordering of the vertices such that every directed triangle are clockwise. Well, I'm not sure anymore now, but you're right.
What are we defining here?
Post-set tournaments. I know this is a good definition, this is the one they use. And I think the other definition is
Okay, yeah.
Sorry. Okay, so they propose this conjecture. That is would be very nice if true. And if it is true, it implies our conjecture that large domination number implies an omega cluster. And so I think that this could be used to find a counterexample to that, because this could very easily be false, and this too. So maybe could be a way to disprove this one. No, let me skip those little 3 lines. It's not that interesting. And okay, so this is the last conjecture I wanted to talk about. And okay, let me skip maybe the complexity. It was long enough to talk, I think. So those are open questions. Some are new. If you like twin width, we were not able to prove that class of tournaments with twin width at most k were chi-bounded. We strongly think it is true, but we are maybe not very smart with 3 width of tournament. We also maybe a question that is that I like, a kind of toy question, is to build some critical tournament for omega. So this would be tournament with omega equal k, but when I delete a vertex, it drops to k minus 1. We have construction for k equal 3 and 4, but we don't have for k at least 5. It should exist. Okay, so this I talked about it already. These two. Okay. So thank you very much. We don't even know what its omega is. So we don't know what its clique number is. Yeah, we don't know if it's between log and polynomial in the number of vertices. So,
Okay.
thank you very much.
Thank you.